Okay, so today I want to do a quick intro to FS2 0.9. So FS2 is the new name for Scala Z Stream. The project was renamed, and probably the biggest change is that it has no external dependencies at all. Scala Z Stream depended on S codec bits for byte vector, and Scala Z for a bunch of things, but for a bunch of type classes basically, and a few data types. So FS2 is completely standalone, no dependencies. There are bindings to integrate it with other libraries, but it by itself is a standalone project. The other thing I want to mention before we get started is that today we're going to be using the 090 snapshot build. It's a little bit newer than the 090 milestone 1 build. So you can effectively think of this as a preview of 090 milestone 2. All right, so to get started, I want to load FS2, the jar files. And there's two projects I want to load, core and IO. The core project is what we're going to spend most of our time in, but the IO project lets us do disk access and network access, and we'll do a couple things with disk access towards the end. The main package for FS2 is FS2 or it's just FS2, and it's common to import this entire package. You can see there's quite a bit of things in it, so we'll just import all of that for the REPL. The types that are in this package are sort of designed to be bulk imported, so you're not going to cause problems if you import FS2._. And for the very first stream that we're going to look at, I'd like to do this example here. So I'm creating this stream using the apply method on the stream companion and just passing 1, 2, and 3. And I get back a value of type stream, and it has two type parameters. These two parameters correspond. The first parameter is the effect that this stream is capable of executing or evaluating. And the second parameter is the output type, the value type of the values emitted by this stream. And so a stream fundamentally is this like mixture of values that we can pull from and like some effects that we can evaluate, maybe to get the next batch of values that we're going to pull, or maybe some effects that we're evaluating just for the effect, like maybe writing to disk or writing to the network. And we're going to see that a lot, like this idea of like we have an effect type and we have a value type, and we're going to need to know what both of those are as we're working through various examples. So here, when we just said stream 1, 2, 3, it's saying that our effect type is nothing. We just had pure values, right? 1, 2, and 3. And so like we're not doing anything special with effects here, and as a result, our effect type is nothing. There's a bunch of things we can do with these types of streams. So let's take stream 1, 2, 3 and just map over it. And you can see we get back a stream of int. Right, and this just works just like normal collections, right? If we called toString on each of our results, now we get back a stream of string. So all the methods you're used to from working with collections should work just fine here with FS2. We can flatmap as well. So if we did like stream 1, 2, 3, flatmap n. And now let's say we did something like use list.fill to create, like if we get the number 3, we're going to create a list of 3 3s. Right? If we get the number 2, we'll create a list of 2 2s, right? Now this won't quite compile because we have the flatmap here where we're returning a list. So is there a way to like lift a list into a stream, right? Just to promote all the elements. We can do that via stream.emits. And you can see the type of what we have is a stream of nothing comma int still. And like flatmap is just going to work sort of like map and then concat. right? The same way that like Flatmap and like vector and list work. Now notice what we're doing in all of these examples is we're just building up a stream. Like we don't know what elements are in the stream, except for maybe that first example. And you can sort of get an idea from the toString that like we're not actually evaluating stuff when building these streams. We're just kind of creating like a description of a program, right? We've got like this segment thing, and there's various functions that are getting called as a result of the things we're doing. So how do we actually apply our description of a program or evaluate our description and actually get values back, right? Well, when we have a stream where the effect type is nothing, we can call toList or toVector. So when this effect type is nothing, we can just say convert this stream, to a list. We similarly could say toVector here. Okay. And so, what are some of the examples we could do with these streams that have no effect that maybe we couldn't do at least easily with collections? So let's do an example. We'll have stream 1, 2, 3, and we'll call that S, and we'll have stream T is 4, 5, and 6. And now what we can do is say stream U is going to be S interleaved with T. Whoops. So we call this function interleave on stream. You can see we got back a stream of ints, but what exactly did this do? Since our effect type is still nothing, we can call toList, and you can see it just alternated, right? It pulled one element from S, one element from T, one element from S, one element from T, right? So it's a sort of a neat way to interleave two different collections, if you will. And you could do that with the built-in collection library, right? Just giving some examples of some of the power of this API. Another thing we could do is intersperse an element. So let's take a new stream, S. And this stream I'm going to create using this range method. I'm going to say let's start at 0 and go up to, let's say, 10. And now I'm going to create another, let's just say, let's create another stream T. We're going to say S dot intersperse. And we'll put, let's say, a -42. And if we look at the result we get here, you can see we had a stream 0 up to 9 inclusive, but now between each two elements, we've inserted this -42 value. And the API of these streams is pretty rich. So if we looked at all the methods, you can see there's quite a bit of combinators that we can use to do various things. And we're going to use a bunch of these today. But I want to do another couple examples with pure streams. So let's take our stream dot range of 0 to 10, and let's just print that as a list. And now I want to take another stream that's just 1, 2, and 3. We could zip these two streams together. And if we look at all these zip methods, there's this one just called zip that just takes a stream, so that's the one we want. So we can say s.zip_t. And if we run that, we'll see we get 0, 1, 1, 2, and 2, 3. So it took the 0, 1, and 2 from our S list and zipped it with the 1, 2, and 3 from our T list. And so zip on these two streams terminates when it reaches the end of either stream, right? Well, what if we wanted to zip S with T, where T just keeps repeating itself over and over and over, right? Instead of just saying 1, 2, 3, and an end, we want to say 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and so on. So this might be a little more challenging to do with collections. And with streams, though, it's relatively easy. We would say s.zip. And now the idea here is we just want T to repeat forever. So we can just say t.repeat. So what t.repeat is going to do is that it'll return a new stream that when it reaches the end of T, it'll go back to the beginning and just do that forever. So the result is a completely infinite stream. But we're zipping the infinite stream with this finite S stream, and so we should still have it end after our 10 elements. So if we run this, let's actually just print line it. You can see it does in fact end, right? My rep will just cut off the output because it noticed a bunch of lines coming out, but you can see it is a list of just 10 elements. And so in the second position where we pulled from T, you see a 1, a 2, a 3, and then a 1, a 2, a 3, and so on. So this notion of like working with infinite streams, but then not completely evaluating them, right? Not evaluating them forever, but kind of bailing out of computations early is a very common pattern you'll see with FS2. So like similarly, we could do something like t.repeat. This is a completely infinite stream, so I wouldn't want to like, just pull from this forever. But we can say t.repeat and then maybe say take the first 7 elements. And now we can call toList on that, right? And this does in fact terminate. So that's one half of the equation, right? That streams let us work with values of a given type. But like we saw, there's the effect notion of streams as well. And all the streams we've looked at so far, the effect has been fixed to nothing. They're just pure streams, just like collections are. But we really want to be able to do things like input and output, right? We want to be able to read from disk or write to a socket or maybe do concurrency or read random numbers, read timestamps from the machine's clock. All types of things that aren't referentially transparent. And we want to do those things in a referentially transparent way, in a pure functional way. And so FS2 provides us a mechanism to do that by working with what we're going to call effectful streams. Streams that have an effect here in this first type parameter. So the effect that we're going to work with today is task. Task is a data type provided by FS2. It's a port of the task from the Scala Z effect library. And it's in the fs2.util or in the fs2 util package. So we're going to import task. Now, before we even get started with task, I do want to point out that FS2 itself is not fixed to use task. The first type parameter can be any effect type. This is much different than Scala Z stream, where Scala Z stream was hard-coded to use task in lots of places. But in FS2, that's been generalized. You could plug in any effect type as long as you have various type class instances available for that effect type. But let's look at task. So a task is a data type that wraps some expression which may potentially not be referentially transparent. And it's a way to wrap that expression such that we can restore that referential transparency. So there's a bunch of different ways to create tasks. The simplest is task.now. And what task.now does, it says, given a pure value, completely pure referentially transparent value, just lift it into the task data type. So if we say task.now, we have that pure value and we get back this t. Now that we have t, we can use this task in a referentially transparent way. We don't know whether this task itself came from a pure value or whether it came from an impure value. But it doesn't matter once we get it into a task. We can do it. We can work with it completely, purely functional, right? So we can map over it, for instance. We could flat map on it, things like that. But how can we work with other types of expressions, right? We could say t equals task.delay. And what task.delay is going to do, we're going to do some I/O. We're going to do something that's not referentially transparent. So we'll say, we're going to write to the console, right? We'll say print line computing value. And then we'll return some value like system dot current time millis. And you can see what we get back here is a task of long because current time millis returned a long. And we could do things like, map over it again, right? It doesn't matter when working with this task t where it's coming from. We're guaranteed that any machinations we do with t are going to be completely pure. Right, so things like map and flatmap and so forth are all safe to call in t. Now notice when we called task.delay, we did not see the print line execute, right? We're lifting that impure expression of print line a value followed by reading the system clock. We're lifting that into this task data structure. And by doing so, we're deferring execution of it until the overall task is run. Right, so we're just kind of capturing that almost like as a callback, if you will, and only evaluating it later. So like, how do you evaluate a task? This like res 29, for instance, we read the current clock value and then added a single nanosecond to it, or a single millisecond to it, right? So how do we actually go about executing that and getting a long back out of a task? And the general idea is that you don't. Or rather, you defer such a extraction until the very edge of your program. So maybe to like your main function, or maybe to like a web tier where you are processing an HTTP request and you get the response built up in a task, and now you want to say, pull the task out, so I'm going to send the HTTP response. But it's all the way on the edge, right? At the very edge of your program. So at the edge, there, you can extract this value, and there's a bunch of different ways to do it. The simplest one is called unsafe run. And so if we just call unsafe run, you can see our print line executed. We have computing value come out, and we have the long value printed. And if we were to call unsafe run again, you see our expression is reevaluated. We get another print line, and we get a new timestamp. Right? These timestamps differ. Right? So every time you call unsafe run, it's reevaluating that impure expression. And looking back at these methods on task, there's a lot of them. The ones that start with unsafe are the ones that you should never really call except for in your main function or at the very edge of your program. But you would never want to call one of these unsafe functions like right in the middle of like a service, for instance. And hence they're prefixed with this unsafe warning. So that was another way to create a task. We saw task.now, and we saw task.delay. Task.now will capture the pure value, and every time we run it, right, every time we run this via unsafe run, we're just going to get back that same value. And task.delay captures like a callback that every time we run it, it's going to be executed. There's a bunch of other ways to create tasks, but the next most interesting, and probably the last one we'll look at today, is task.apply. So here I want to do the same example. And say that when we call task.apply, we're going to print line computing and then run system.current time millis. And when we try to compile that, we get this warning or this error that says, in order to call test.apply, we need to have a strategy in scope. So a strategy is FS2's equivalent of a thread pool. So let's take a look at strategy. We're going to say implicit. We're going to put this strategy in implicit scope, right? We're going to say implicit val strategy equals strategy dot, and then let's look at our options to create strategies. We could create a strategy from a Scala concurrent execution context. We could create one from a Java util concurrent executor, or we can create one directly, either as a fixed thread pool of n threads, or as a thread pool that adds threads on demand as long as there's work to do, but then keeps those threads running for a little bit in case more work comes in. So for today, I'm going to use the from fixed daemon pool, and we'll create one with 8 threads. So now when we run task.apply, this executes okay. So if we run t.unsaferun, you can see not much looks different here, at least at the REPL. So what's actually occurring? When we did task.delay, the result of calling t.unsaferun was that our callback that was captured in task.delay ran on the same thread, ran on the current stack frame of unsaferun. In this example, though, we did task.apply. And so the idea here is that when this task is run, it's going to submit a job to the strategy. And that job on the strategy, when it executes on the thread pool, is going to evaluate this value, this expression. And then when it finishes and comes up with an answer, it's going to send that answer back to whoever's asking for it. Now at the REPL, we're calling t.unsaferun, so we're blocking. We're saying we need the result of running this task. Give us the result. And so the REPL is effectively blocking here and saying, wait for that task running on the thread pool to finish and give me its value. And we can observe this occurring if we were to print the thread name here. So if we changed our print line to computing on, and then said thread dot current thread dot get name, I think. If we do t.unsaferun, we see that it's computing on the main thread. And so our task.apply is not actually even being run on our strategy in this case, I don't think. Let's try task.delay. So in this case, both of these are executing on the main thread. So what I said is not accurate. Instead, what's really happening here is that task.apply is capturing that strategy, and we'll use that strategy to execute any asynchronous aspect of this task. But this particular expression ended up being synchronous, and so this one was executed on the main thread.
How does it know that?
What's that?
How does it know it's asynchronous versus synchronous?
I mean, it doesn't. It's based off of the expression itself. So the code that is passed to apply, this bival, yeah, I don't know. That should have worked. Yeah, that should have worked. I'll look into this. This might be a bug. Let's try one other thing. Let's do task.start. Yeah, so it is what I, so basically what's occurring is that the callback we're passing to task.apply is running on the callers thread. But if we explicitly fork it off to a strategy using start, then it is running on the strategy thread. So I do think this is a bug in apply, but I'll double check. Okay. So moving on, let's create a task that gives us that timestamp. So I'm going to create a task called current time. It'll be task of long, and I want to say task.delay of system.current time release. And now, can we use this? How do we use this task in a stream? Let's take the stream object and call the eval method passing current time. And actually, let's look at the signature of eval first. So eval takes an f of a and returns us a stream of f and a, where f is the effect type and a is the value type. So we're saying, like, evaluate this particular effectful value, and any of the pure values that come out of it, make those the output of my stream. So if we evaluate current time in stream, we get back a stream of tasks come along. What if we tried calling like toList on this? We get a compile error, right? Because toList and toVector that we used earlier only apply to streams that have no effect, where that first type parameter is nothing. Here, if we call toList, it complains because our effect type is task. So how can we run such a stream? There's a series of methods on stream that all start with the name run. To get started, we're going to use run log, which says run log is going to return us a f of vector a. So basically what it's going to do is gather up all of the outputs of this stream into a vector, accumulate values into a vector, and then return us that vector inside our effect type. So if we call run log, you can see we get this task of vector long. Now, current time was a task that when we evaluated, it returned just the time of the system. And we're evaluating it one time. So when we run this overall task, we should get back a vector with one element in it. And if we run res56.unsafe run, you can see we get back a vector with one element.
Right?
Yes?
If you did a repeat on that stream, run log would never return anything, right?
Mm-hmm. Right, so run log is actually kind of a dangerous operation, because if you have an infinite stream, it's never going to return. It'll just dump heap. Right? You'll eventually run out of heap space as it's accumulating stuff into this vector. I said streams themselves are pure. They're purely functional, right? So any calculations we're doing here, even though we're doing things like reading, reading an impure value, a clock value, we can refactor streams and combine them and compose them without worrying about any type of impurity, right? The effect type and the stream type is going to manage those types of issues for us. And that's why when we called run log, we got back a task, right? We didn't get back a vector of long, but we get back a task that we still have to go and execute impurely somewhere at the edge of the program. All right, so let's do what Mike suggested and add repeat here. But now we don't want to call run log just like this, because it'll fill up a vector and eventually run out of memory. So let's just say let's take 10 elements. Let's take 5 elements. You can see we get back the same expression, task of vector long. And if we unsafe run that, we get back 5 values. You can see the first 2 had the same clock value, and then we got 3 more. We read the clock value 3 times from the system, but it was all in the same millisecond. This notion of starting with some impure expression that's wrapped in task and continuously evaluating it forever is pretty common. So there's a combinator for it called repeat eval. And repeat eval always returns an infinite stream, as long as there's no exceptions thrown in the evaluation of your impure code. An infinite stream that's just continuously always got a value available. Oops. Okay. And so the things we did earlier with pure streams still apply here. So for example, let's take a stream S and say it's the numbers 0 up through 8. And now let's say we want to zip that stream with timestamps. So we can just use the same exact zip combinator we used before, and we'll say zip with stream.repeatEval current time. Now you can see what we get here is a stream. The output type is the pair int and long, right? The int from the stream S, and the long, which is the current time when that value was computed. But notice that the effect type has been promoted to task here. Even though S was a pure stream, a stream that had no effect, because we zipped it with an effectful stream, that got promoted to the task constructor. And so now we can no longer call like res63.toList, right? That doesn't exist because we've got an effect sitting there. But we could say run log and maybe .unsafe run. And so notice, like, even though we had this infinite stream, effectful stream of timestamps, because our S stream was only limited to 8 elements, the same example from earlier where we zipped with an infinite pure stream, that same behavior works here for effectful streams as well. Okay, so let's do a bit of a more complicated example. What I want to do now is use the FS2 IO package to read a file. So if we type IO dot, we can see we've got, at least as of right now, we have a file package and a TCP package. We'll at least have a UDP package before the release, before the final 0.9 release. So if we say io.file, we can see there's this read all method. Read all is going to take a path to a file to read and a number of chunks, or how many bytes to read at a time from that file as like a chunky I/O input. So the first argument, the file to read, I have a file here in the same directory called Fahrenheit.txt, and it's just a bunch of either blank lines or lines with degrees Fahrenheit. And we're just going to read that in and process it in a pure way, in a referentially transparent way. All right, so to do that, we're going to need Java and IO file paths.get, and we're just going to say Fahrenheit.txt. That's the file name we're loading. right? So this is just the Java 8 file API, the way you refer to a file name on disk. That's not like opening a file, right? It's just a file name. And then let's say we're going to say read chunks of like 16 bytes at a time. I mean, normally you would want this to be like 8K or 16K or something, but for now, let's just do 16 bytes at a time. And we get this error message that says it can't find an implicit value for parameter f of type effect of f. So this is kind of interesting. It's saying that in order to call read all, you need an effect type class instance for the effect parameter, for your f parameter. Can't quite convince Ammonite to give us the signature of read all. But what you'd see is that it looks basically like read all f, where f has an effect type class instance.
What's
that?
What if you just typed in read all space underscore? I think it would give you the type then.
No, same. But yeah, I mean, so the signature of read all is effectively it takes one type parameter, higher kinded, that requires an effect instance, and then it takes like the file name as a path and the chunk size as an int, and returns us a stream of f comma byte. Right, all of the bytes of that file we're going to stream out off of disk. Okay. So if we try our example, what it's complaining about here is it's saying that, hey, I don't know what f is, right? That like I have this type parameter f, but you haven't told me what it is, and so it must be nothing. But now it can't find an effect of nothing in scope because nothing is not an effect. So the error message is kind of annoying, but really what it's telling us here is we have to specify what effect do we want to read from disk in. We want to read in the task effect. We're going to use task to do our file I/O to lift these impure expressions into the pure world. So if we say that we want to read using task, then we get back our stream of bytes. Okay, so let's call this source. So source will be our stream of bytes. And now we can do all the things we did before. So we could call run log dot unsafe run. And there's our bytes, right? Ammonite cuts us off. It only prints the first 10 elements. But if we did like res67.size, you can see we've got 3,000 bytes in the file. So are there things we can do with a, what other types of things we can do with this source, this stream of bytes, that lets us get access maybe to the, like the Fahrenheit values from it, right? So source here is a stream of task comma byte. And FS2 has a text package. And we've got methods like UTF-8 decode. So UTF-8 decode returns us a function from a stream of bytes to stream of bytes, and it's not really nothing here. This is just a REPL artifact. But if we look at the source or we look at the docs, what it's really returning here is a stream of any f comma byte to a stream of the same f comma string. It's a free variable. It's an unsolved variable that anything can be put there. So like, how can we use text.utf8 decode with our source? Well, one option is we could just say text.utf8 decode and pass it source, right? Because this UTF-8 decode method is returning us a one element function, like a function one. And so if we do that, we get back a stream of task comma string. And we could type res70.runlog.unsaferun and see that we are getting the file contents. And notice we're getting it in like these little short chunks, right? Because we said only read n bytes at a time, like 10 bytes or whatever it was. And so we're getting little chunks of the file. There's another option, though, which is more idiomatic with FS2, and that's the method that's called through. So there's a bunch of different variants of through. The one we need right now, though, is just plain old through. So if we were to do runlog.unsaferun, you'll see we get the same output. So this expression of source.through one of these functions is really just the thrush operator, right? It just reverses the order of the function application. So if anyone's used like the thrush operator from Scala Z7, right? Rather than writing like f of a, you could write f, pipe greater than, a pipe greater than f. Right? It was just a way to kind of change the syntax a little bit. Well, source.through is really just the thrush operator for streams. But we provide it because it's very, very, very useful. It's very common to write the stream out this way because you can describe your transformation in a very natural way. In a very like left to right sort of way. So what is text.utf8 decode? We saw that it was a function from like stream to stream. But if we were to look at the text package, you'd see that it's really defined as something called a pipe. So from a model perspective here, what we're saying is that if you have a stream, you can pull elements through a pipe. And what that pipe's going to do is it's got an output type of type string, and it has an input type of type byte. And you've got to hook up a stream that can output bytes into the front of this pipe. And as long as you do, then when you pull elements through the pipe, you're pulling strings out. Right? That's sort of the idea here. So what is a pipe really? A pipe is defined like this. So a pipe is a function from stream to stream where it can be defined for some effect type. It's got an input type and an output type. Right? And then the definition itself is just that alias for our stream function. So that's why over here in our example, we use this through method. We're kind of evoking this notion of pulling elements through a pipe. Okay. So res74 is sort of annoying to work with, right? We've got all of these strings. What if we did like res 74.runlog .unsaferun, and so now we get this vector, and then like ask for the size of that vector. You can see our vector has 193 strings in it. We knew our file had about 3,000 bytes in it. So like what are these 193 strings? Maybe that's one per line, right? If we were to look at Fahrenheit, we'd see that there's actually more. There's 675 lines in this file. If we were just to take like an arbitrary value out of this returned vector, I don't know, let's say like 100. What's the string 100? You can see we're getting a little chunk of the middle of the file, right? What's the one that's like 101? You can see we're getting like, you can see the previous one ended with a 1, and then the next one starts with a 9. And, like we're sort of getting like this like random chunking. And that's because when we did our source, we said read 16 bytes at a time. And then when we fed that source through the UTF-8 decoder, each chunk of 16 bytes that we got output was decoded into strings. But now we sort of want to stitch all that stuff back together. And so we've got a bunch of different ways we can do that. Let's start with saying, here's our source, or through our UTF-8 decode. We could join all of these elements together into one big huge string, but now that huge string is not going to be delimited on individual lines. Right? We're just going to have one big flat string that's got like, /r's, /n's throughout. We don't really want to do that. We want to be able to process this file incrementally, a line at a time. Because if we were just to do something like what I just described, right, decoding all of it, pushing it through run log, actually executing our effect, and now like joining all of these together, which if I have like a vector of strings, I want to make one big string, I can just do make string, right? You can see like I'm already sort of violating the rules because now I'm doing computations after a call to unsafe run. And we should never really do that, right? Unsafe run should always be at the outermost edge of your program. Never, ever call it anywhere else, right? But let's just say we're going to ignore that for a minute. We call make string. All right, so now we've got our entire file into a string with all the new lines all throughout, and we could do like regular, Scala like string manipulation to start processing this in an incremental way, but we've already loaded the whole file into memory. And we don't really want to do that. We want to work with this file incrementally so that if it's like arbitrarily large, right, millions and millions of elements, everything works out. So we don't want to leave the safety of the stream world. So instead, in order to handle this like chunking issue of our chunks not matching up with lines, FS2 provides another pipe that lets us reconstitute lines from a stream of strings. So we're going to say through again, and this time we'll say text.lines. Right? And if we were to go over for a moment and look at the text.lines definition, you can see the text.lines definition is a pipe that says for some arbitrary effect f, it doesn't matter what f is, you feed strings into it, you get strings out of it. And all it's going to do is like realign those strings such that the output is always one full line from the input. So let's try it. If we run this example, you can see now we get a vector, but each element in that vector is a separate, independent line from our input file. Okay, so that's kind of neat. What about the fact that we're reading a file throughout this stuff? What's happening to like file handles? And the answer is that FS2 manages resource allocation and finalization, like freeing or closing a file handle, automatically for you when using things like this io.readall or io.file.readall. And it does it in a way that like the power of that resource acquisition and tracking is available to you as well for your own arbitrary streams. So like FS2 itself doesn't know anything about files or doesn't know anything about like TCP sockets. The core of the library knows about this general notion of resource acquisition. You can build very, very, very complex streams, right, with all sorts of crazy pipeline stages and all sorts of strange asynchronous behavior. And even in the most complicated stream you could possibly imagine, resource acquisition and cleanup is still guaranteed by FS2, even through refactorings of streams. Even in presence of exceptions, right? So even if you were like map, map over some line here, and then throw an error, even then, resources have been cleaned up successfully. Our exception bubbles out to us, of course. We get our oh no exception when we call unsafe run. But the file handle, if you will, the resource that we opened with the operating system has been freed by the time we get this runtime exception. Okay. So I want to do a couple other things. Let's take this definition here of this function that converts a Fahrenheit value to a Celsius value. So now that we have that, we can just map Fahrenheit to Celsius over our input. Now, this is not quite going to compile because we've got individual lines here, which are strings, and Fahrenheit to Celsius wants an input of doubles. So we want to map here and say to double. So that looks reasonable. That compiles okay. If we get a line that's not a double, what's going to happen? This to double call will throw an exception. And if you look carefully at the output earlier, one of the first lines of the file is a comment. So if we're to run this, you'll see we get an exception. And the exception is that number format exception, right? It's saying the string, and here's our comment, is not a valid double. So even though an exception was thrown, our file was closed successfully, but this isn't really what we want to do, right? We want to be able to skip processing of these comments. So how can we do that? Well, before we call to double, let's call filter. So we're going to say get rid of empty lines. There were a bunch of empty lines in our files. And get rid of lines that start with a comment. Okay. So let's start. Let's break this up a bit. Oops. Maybe I can't do that at this point. No, it's not going to let me. All right. But we filtered out those bad strings. So now if we were to run this, you can see we get our Celsius values. Okay. So now what do we want to do? Now that we've got Celsius values, let's put these Celsius values back into strings. We have our stream of task string now. And now that they're strings, we want to stick new lines in between each element. And so we can use that intersperse method we saw earlier. So we'll intersperse with new lines. Let's run it again and see what we have. So what we have here is a vector that starts with a Celsius value, then has a new line. That's what this next string is in the vector. It kind of prints a little bit weird because of the way the REPL prints new lines. But that's really just a string that's got a single new line in it. Then we have another element, and then another new line, and so forth. So now that we have all of these strings, we want to write them all to disk. And so let's look at our IO file package again. And there's this method called writeAll. So writeAll works very much like readAll did, where it wants a path to a file. So we can say Java and IO file.paths, and the path of the file we can just say is Celsius. Now writeAll has the same complaint here. Like it says, I can work with any effect, but you got to tell me what effect you want me to work in. So we'll say, okay, well, we want you to work in the task effect. And now what do we get back? Rather than just getting back a stream, writeAll is giving us back a pipe. right? A pipe that says, you feed me the input of bytes, you give me bytes, and I will output unit. So this is kind of interesting, right? That as you feed bytes into this, this pipe, it's going to give you back just unit values that you can't do anything with. So why would you ever do that, right? The idea is that you're doing it because of the effect that's going to be occurring when it's evaluated. That you're writing files to disk. It's something that you're not going to return to the end user. But as these bytes come into this pipe, they're going to be written to disk. Okay, so how can we use this with our big pipeline we're creating? Well, at this point, remember, after we interspersed our new lines, we still have a stream of strings, right? The expression here was still a stream task string. So we want to push that through writing this file. But we're not going to be able to because, string doesn't match byte. Okay, and so what it complains about is that it's saying that it found a sink of bytes, but it required some pipe that can read strings. So now what is a sink? A sink's a new concept. Let's go back and take a look at our definition of pipe. Here's our definition of pipe. Remember, it was a function that, a function from stream of fi to stream fo. And a sink is really just a pipe whose output type is unit. So sinks are wildly different in FS2 than they were in Scala ZStream. So back here, what it's telling us is that, hey, this write all thing is really just a sink. It's one of these pipes who have an output type of unit. And your input just doesn't match, right? Like your input of write all is a byte, you're outputting a string, we have a problem. So we can't quite use write all yet. Instead, we can use text.utf8 encode. So now we get back a stream of task comma byte. And then from there, we can say through again, io.file.writeAll. Okay. So at this point, we have an entire program that can open a file, process the lines in the file incrementally, converting the each line into a value, and then writing the contents to disk. And this would work on a file that's 100 gigabytes large, right? Because it does this in an incremental fashion. We didn't code anything for incremental fashions here, right? We didn't do anything with like buffers and pulling from file handles incrementally and moving the buffers along through our pipeline. FS2 is able to manage all of that from this much higher level description of what we want or how we want to transform our data. And notice that this whole thing we did here, this whole pipeline we created, it ends up being a stream of task comma unit. Right, so our program, if you will, is this whole pipeline. And we've created this stream that never has any output, that the only reason we're ever going to evaluate it is to cause this transformation to occur, but we're never going to look at a value coming out of it. And so it doesn't really make sense to call run log here, because we'd be giving back like a vector of unit, right? But we don't want like a vector of unit. These units are meaningless to us. We don't care about the output. The output, the real point of it is writing to that file on disk. So instead, we just want to call program.run. And we get back this task of unit. Now I want to look on disk here. You can see I only have a Fahrenheit file at this point, right? Because everything we're doing, we've not executed anything that writes to disk yet. Even this program.run, really just gave us our program wrapped up inside of an effect. Right? Everything's completely referentially transparent. There's no I/O occurring. And only when we say res99.unsaferun do we have our Celsius file created. Right? So this is the general idea behind FS2. This is the first example of doing, full I/O, file-based I/O. There's a lot more to the library, and we'll probably have additional sessions in the future. But specifically, the asynchronous portion of the library is extremely useful. And everything we did here today was complete synchronous work. So anyway, that's what I wanted to cover for today. Does anyone have any questions?
Hey, Mike?
Yeah.
I was wondering if you have time to go over the pipe that did the, I'm blanking right now. It wasn't the first through, but the second through. That took all of the UTF-8 decoded string chunks and turned them into lines.
Right.
Like if you were to write that yourself.
Yeah. How would you do it?
Right, exactly.
Right. So like, how do you write a pipe? That's a really good question. So let's talk about text.lines. We said text.lines is a pipe that reads input of strings, then output strings, right? And the effect type can be arbitrary. So the REPL here just sets it to nothing, but it can be anything. So what that really means is that like this text.lines has this signature, like a stream of some arbitrary f comma string to a stream of an arbitrary f comma string. So how would we write such a thing ourselves? So here's effectively what we're trying to build. This mylines function that works for NEF. Because of the way pipe expands into this function of streams, we would typically write something like this, right? We would define mylines as this function of the input stream to some output. And now the idea is we want to pull elements from the input stream and then transform them. So how do we pull elements? Well, I'm going to do a shoddy implementation of mylines because it's easy, and then a real implementation I'll show you. But to pull elements, we could do something like in.map. Like just define our output stream using functions that exist on the stream class, where this in is like, is this input stream here. So how could we do that? Well, we've got some arbitrary s, and if you look at the string class in Scala, or like you look at like the rich string object that decorates string with all the Scala specific methods, there is an s.lines method we can call, which will split a string into an iterator of string. So this won't quite compile, right? It's going to say, hey, wait a minute, you're calling map on a stream of string. You got to return strings inside a map, and you're returning me an iterator of string. So we could change this to Flatmap. Still doesn't quite compile, right? It says Flatmap requires you to return a stream of strings, but you're returning an iterator of strings. So we can convert our iterator to a list and then use that function we saw earlier, stream.emits, to say lift that list into a stream. And now we have our myLines function defined. So does it work? Let's try like hello \n world, right? So we've got a stream of one element, and we put it through myLines, and then we call toList. And we have no effect type here. This is just a plain old, pure stream. Now, unfortunately, this isn't going to compile with a nasty error message because Scala doesn't like to infer nothing. And so basically what it's happening is that it sees that this input stream, its effect type is nothing. But then it sees that like through in myLines works for an arbitrary f. And Scala says, oh, well, I really don't want to infer nothing for that arbitrary f. And so it refuses to and gives you this nasty error messages. So the typical way to fix this, there's this method called pure, which lifts a stream of nothing to a stream of pure, where pure is a special type constructor that exists in FS2 to work around this limitation in Scala's type inference. And you can see then our output is what we wanted. So that it worked in that example. What if we what if we put a stream of 2 strings as input? Hello world, this works, right? That looks good. What if we did 3? Oh, now we have a problem, right? What happened in this case? Well, our algorithm assumed that each string in the input, like all it did is took an input string and split it up into all of the constituent strings that made up that input string. But it didn't handle the case where we actually have a string that spans, like a line that spans 2 strings from the input. So like the word this, there's no new line between H and I, right? It's just a spanned value. And so of course our algorithm doesn't know about that and outputs them as 2 separate values. So in order to solve this the right way, it's much more complex for this particular algorithm, right? Some pipes you're going to write are as simple as writing the one we wrote. Like use the input stream and just apply an existing combinator to it, like map or filter or collect or Flatmap or whatever. But in order to do it right, you kind of have to like pull elements from the input one by one and like sort of maintain like, where the new lines are and when do you output values, things like that. Does that make sense?
Yeah, I mean, you just now hit on the thing that I was mostly curious about because, because of the fact that you were chunking it in 16 bytes at a time originally, I was wondering, when you split that, how do you do that? And so that was the part that I'm mostly curious about. But if it's a larger conversation, we can come back to it at another time.
Yeah, the lines implementation, text.lines, is ridiculously complicated because of all of the crazy edge cases you have to deal with. Like this is just one of the edge cases, but there's lots. Let's do one example though of something much simpler. Let's define my take. Right, so we want to say my take is a pipe that reads n elements from the source and then terminates. So we're basically just re-implementing take from FS2. And this is, of course you could implement this with take, but that defeats the point, right? You could just say like _.take n. And actually, let's start that way just to show that it works. If we said stream dot, range 0 to 1,000 dot take, dot through my take 3 dot run log. We don't have to run log. Dot to list. Oh boy. Because we need pure. That does in fact work, but how could we do that? How could we implement my take if it wasn't already built into the library? That's sort of the exercise, right? So let's do that real quick. We can do that in about a minute. So the idea is that we want to pull elements. We're going to define this recursively. So we're going to pull elements until we reach like n equals 0. And so like one sort of intro implementation or initial implementation of how you might want to define this is like this. The idea is that we're going to use the input. And we're going to pull on it. So pull is a method that takes takes a value of type, it takes a function from something called a handle to a value of type pull. So I'm going to represent that with this function called go. So I'm going to write a function called go here. This function called go, its input is a handle. So what a handle is it's something that lets us pull a value from the input source. So it has two type parameters. It has the effect type parameter that we're working in, and the type of value you're pulling from the source, in this case, type A. And our pull function, I said, its argument was a function from handle to pulls. So a pull in FS2 is a data type that has an effect type F, which needs to match the F we're using everywhere else, that outputs a certain type. So we're going to output A values. And that then has like a resource that you can sort of like hide away and then reference when you need it, which we're not going to need. So we're going to set the resource to unit. Okay. Now, how are we going to implement this? So this is another function here where we're returning this function 1. So we're going to say, give us that handle H. And now on H, we want to like receive a single element from the input. And so we're going to call receive 1, which says just receive 1 element from the input. And now here, we're going to pattern match and say we got this single element of type A, but then we got like a new handle. I'm going to call it H, so I can shadow this H out here. Like this new handle represents any remainder, like what's remaining of the input, right?
What's with the hashbang colon syntax?
This is an alias for a type called step. So you could write like case step A comma H.
Every time I see that, I think that they're trying to do some sort of type description.
Oh, that's funny. Yeah, I never thought about that. And you can write like this step A comma H thing. That should work. It's just not common. You will see like all throughout the internals of FS2 it written this way. But it's just a pattern match, right? It's just saying like what receive 1 is returning us is a value of type step. Step's a case class that's got like the value that we received, and then it's got like a new handle for all the remainder. So what we want to do is like, since we got a value A, we want to output it to the output of the stream. So there's a constructor for pull called output 1 element. Now pull's a monad, so we can call Flatmap on it. And because if we just, well, actually, this is a good example. Let's just stop here. Let's just implement it that way. We have everything we need at this point as far as types are concerned. We output a single value. This pool.output1 is going to return us a pool of FA unit. So this all should compile, even if it doesn't quite do what we want yet. Right? So there's my take. But if we stick, if we run it through this example here, so I want to do that. It's going to just run. It's not going to do exactly what we wanted. So what did it do? It output a single element and then stopped. And that sort of makes sense, right? Because we're saying when you call my take, open the input stream, pull on it with this function called go. Go is going to receive one element from the input and then output it, and then we're done. And that's why our output overall was just the value 0. So our definition of my take needs some more work, right? What we want to do is say after we output this element, we want to, sort of call ourselves recursively, or we want to call ourselves recursively with one less n. But now, what about n? We haven't even looked at n yet. So, can we somehow call my take recursively from right here? But we have a problem with that because my take is a pipe, but here we need a pull. And so, really, we kind of want to restructure this a little bit and say, well, what if go tracks the n value? If we do that, then we need to initialize it to n that comes in from the function, right? So this n here is in scope down here, and we're passing it as the initial value for go. But now we want to check n, right? We want to say that, in the body of go, if n is less than or equal to 0, we're done. So just say pull.done. And only otherwise do we want to receive an element. But now, we've got a little bit of a problem here because go is saying, if we hit this first case, just return a pull. But we really need to return a function from handle to pull. So we can just say, here we could say underscore arrow pull.done. Right? Or we could say h arrow pull.done. But if we're going to do that, we might as well move the function part up and out. And we'll say h arrow here, and then open brace. Right? So now we've got our handle h right away, and now a whole body of the thing that needs to return a pull. Okay, so we've got our base case, our termination case of our recursive function done, but we still haven't called ourselves recursively. So let's go to our, after we've output the value, how can we call go again? What we want to do is call go of n-1. But now go itself is a function from handle to pull. And down here, we just kind of loosely know that we need to return a pull. Right? We don't know how to put together an output 1 and another pull yet. But we know that we need pulls down here. That's the goal. So, if we call go recursively, how do we feed it a handle? But we have a handle here, the remainder. So after we've read one element, we got this new value of h, which was the remaining part of the stream. And so we can feed the new h here. And that's why we use this name h, by the way. We shadowed the outer h on purpose so that we could never accidentally pass that outer h recursively, causing an infinite loop. So this is cool. We've got this pull here, which is a pull of f, a, unit. We've got this pull here, which is also a pull of f, a, unit. We want to combine the effects. We want to say, do the output, but then also do the recursive call. So how do we put these two expressions together? And we can do it via Flatmap. So we're just going to say output 1 is going to output us a unit. That's what that resource thing's about. Like, it's going to output an A out to the stream, out to like where, you know, the person who's receiving our stream or reading it from us. But when you Flatmap on it, you get access to this special resource value that's like hidden in there. Well, we don't really need a unit, so we're just ignore the input. But we're going to return another pull of the same type. And that should be the whole implementation then of my take. So like one little thing to clean up is that like, look at this pattern. And actually let's put some more new lines in to help read a little bit. But look at this pattern here of we have a pull and then we call Flatmap returning another pull. And we don't use the value we're flat mapping over. Right? We're only doing these two flat maps to accumulate the effects of both writing to the output and calling ourselves recursively. So there's syntax for this, like well-known syntax, right? It exists in cats, it exists in Scala Z, and it exists in FS2 on pull, which is to say instead of writing flat map and then ignoring the input, just use this and then operator, which is greater greater. And it's pure syntax for a flat map that ignores the input. So finally with that, that's how you would implement like your first version of my take, basically. So if we did our example again using my take, you'll see it now functions. And so this whole pattern of like writing these recursive functions, right, in order to implement pipes is an extremely common way to implement your own pipe. It's one of the most important patterns to learn if you have to write custom pipes. Yeah. Does that make sense?
Yep.
All right. If there's any other questions, I'll take them now, but otherwise, thanks for coming.
Thanks, Mike.
Thanks.